We're given a limit. Nope. We're given an infinite series. And to be honest, I might just start writing sigmas and not have to do the bounds because it's always going to be from 1 to infinity, at least for testing convergence and divergence. If it's not, then I'll make a point to make a different bound. There are a few that we have to be careful of this chapter from another book. It's like brother from another mother, but chapter from another. My brain's if we evaluate the limit as k goes to infinity or n goes to infinity of a sub k or a sub n or a sub I, whatever, what are we taking the limit of? Is it too small? What are we taking the limit of? We have to be precise in what we're doing, or at least in you guys knowing what this is talking about. So we have an infinite series, right? Series, sigma, additions. The sum. What is this having us evaluate? The limit as we go to infinity, looking at what? The what? Not the right word, but yes, Kevin's right. It is the function, it's the argument of the sigma. But what is that? Section 9.1, what did we learn? Sequences. Not series. Exactly. So wait a minute. How can we determine something about the infinite series if this is taking the limit of the sequence of terms? Not series. If we take the limit as we go to infinity, if we look at the sequence alone, there are 3 possibilities. That's what this is saying. Okay, so we're needing to think about the series, the infinite series. If we look at the sequence, what could be true? Well, either that limit does not exist, like an oscillator, right? An oscillator that's not going to 0. Which it could literally not exist. So we could have an oscillator not going to 0. I should say an alternator, huh? That's okay. An oscillator not going to 0. Or we could have positive infinity. Or we could have negative infinity. All of those, what's true? Nth term test says divergent. Good. Or we could have the limit actually equaling a constant. We could have it equaling an L that is not 0. According to the nth term test, also divergent. But what if the limit exists and the limit equals 0? We don't know anything about this series. But what does our forever card tell us about this sequence? Convergent sequence. But what about the series? Nothing. Nothing. And what do we literally put on our endeavor card? We know nothing. The limit equals 0 of the sequence, we know nothing. Because for the series, we are needing to figure out what is going on as the limit goes to infinity of the partial sums. This does not answer that question. There is a snazzy divergence test that says, oh, but I know what's going to happen to this if he equals DME, positive infinity, negative infinity, or any number other than 0. He's anything but 0. I know that that's going to diverge. But if he's 0, I don't know. Sorry, just kidding. Maybe, maybe not. That's it. Okay? That's the nth term test. That's the divergence test. Oh, scroll down. Okay, what was the other test that we saw yesterday besides the nth term test, besides the divergence test? The geoseries. Remember? They're up on the board. 2 tests. Every section. Pretty much 2 tests. So geoseries. That was back from pre-cal. And I'm just regurgitating because some of you guys were gone yesterday. Yes, you should have watched the video. But just a reminder before we tackle today. Geoseries. Geoseries, well, an infinite series only is a geoseries if the terms differ by what? If the terms differ by a common ratio. And that geometric series, the terms differ by a common ratio. Differ meaning not difference as in subtract or add, but differ as in a multiplication or division. of a common ratio, then Kevin was starting to get us on the track of convergence or divergence. When will a geoseries converge? When its ratio is between -1 to 1, not including -1 to 1. And when will a geoseries diverge? When the common ratio is greater than or equal to 1, or less than or equal to -1. Yes. And with the geoseries, do we have something that we can say the geoseries converges to? No. Diverge. Yes. Not sequence. And we have the sum. I saw or I heard someone doing homework last night being like, wait a minute, how do we find the sum? What's the only way that we know how to find the infinite sum right now? If we have a geoseries, if it's a converging geoseries, then we have a formula. Otherwise, we have no clue. Unless we get a calculator out and we start playing around with our sequence mode and hope that we can see what it seems to be converging to, and then make a conclusion, hoping that we're right. It's a lot of hoping. Okay, so where did we leave off yesterday? Right about here. If you guys want, you can just write a sigma, and you can assume it's going to be from 1 to infinity. If it's never not, then we'll change it. Or we'll specify it. All right, what do you guys notice about the first one? The first one today, number 3. What do you see? The degrees are tied, so therefore, since is or is not 0. So what does that tell me? By what test? Answer. Am I kidding about writing the test? No, I'm not. Why? Because I'm making you study them every time we're doing anything. Okay, how about the next one? Infinity? How do you know? That's not indeterminate. 2 to higher and higher and higher powers. What's happening? But yeah, growing and growing and growing, right? So can I say that's equal to infinity, which is not 0? Yes, I can. Since it's not 0, since it's not 0, I can make a conclusion. Otherwise, I would just be like, oh, never mind. So, not equal to 0? Cool. Since it's not equal to 0, what's going to happen? About the next one. It's getting kind of boring, huh? What's the limit?
0.
Whoop. But e to an exponential function is the strongest one. Except for factorial. Wait, but the special converging sequence, wasn't it e to the n, not e to the 2n? Couldn't I just make that e to the n squared? Or couldn't I just make that e to the n times e to the n? Either way, bottom wins. Either way, bottom wins. So if bottom wins, why didn't I write a since? I have no conclusion to make. So right now I just stop and I say we know nothing. Why? Because I'm not able to use this test. The only thing this test does is prove divergence. So I don't know. I tried the test and the test failed. I tried, hey, where else in calculus do we sometimes try a test and the test fails? And we might have to go back to some other test. Second derivative test. What are we testing for? Relative extrema, relative mins and maxes. When would the second derivative test fail? When the second derivative equals 0, which means there is no concavity, which means, oh, I can't tell whether it's a min or max by testing the critical number there. I'd have to go back and look. Maybe it's an absolute value function that has no concavity, but is still a thing. Good job. How about number 6? A half? How is Lorenzo saying a half? Is it a true tie? Yes. Be careful in homework. There might be a couple that you think are ties there. Huh? Or you might think they're a tie, but you come up with the wrong limit. It's approaching. Remember, if this was some sort of bless you, FRQ, logic would have to be seamless. Which means if you're ever in question, I guess if it's one of those, you're like, I don't want to lose a point and it's an FRQ, couldn't you just say, I'm pretty sure it's not 0? I guess you could do that and then not be wrong. But they were right. It was 1/2. It being the limit of the sequence. Which is not 0, so what am I going to come back and do? Since that's enough, I can apply my test. So the we know nothing, guys, that's not applying the test. I mean, it is. It's trying the test, but the test is failing. It's not showing us anything. Please, 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 you have to internalize that. Every year in BC, I have kids come to the quiz on Friday, and they say equals 0 converges. And I'm like, well, wrong. Not necessarily that many wrongs, but at least a few, so please be careful. So how about number 7? Wait, I heard 0 and infinity. What? What's the limit? 0. Here's a special one. I haven't mentioned that I haven't told you why. A good question. Is the limit 0? So what do I know? Exactly. So when does the nth term test, when is the nth term test able to be applied technically? When the limit of the sequence is anything but 0. The limit of the sequence is anything but 0. But to know that the limit is anything but 0, you have to know how to take limits. Hey, good thing we just did our chapter 9, which was kind of an awkward, let's do more limits chapter. How are we doing? We doing okay? Oh, well, then what are we supposed to do today if that's it? So then play with this one. AJ, you're welcome.
Oh.
Fuck. I'm not so much worried whether or not you guys would get the final conclusion of this being divergent, which it is. I'm more concerned that you might accidentally write the wrong limit, and so if it's an FRQ, you might get it wrong, or at least get points taken. If you did not equal to 0, could you be right? Meaning you would be right. I think it would be enough. But if you were seeing this in a L'Hopital's problem, or maybe in like a limit problem where the answer is the limit itself, because they have been putting limits every now and then, more recently at an A or a B in an FRQ. Let's say it wasn't a convergence. Let's say it was just a limit. Would you know the answer to this was 1/2 and not 1? Why? Are these tied? Now they are. Were they before? Technically not. And so you rewrite it. What's the ratio of the leading coefficients? This is not properly written unless you put the exponential piece. Well, this is addition, so he's just separate. But the exponential piece with his proper coefficient. Ooh. What's the ratio of leading coefficients? Was it not equal to 0? Yes. Because of that, can I say that it diverges? Yes. I'm just more concerned as to whether or not you would have known the limit was 1/2 and not 1. Oh, I just took away one of the most fun homework ones. Are we okay? Okay. So, to that end, nah, we're not doing, ooh, there was a good one. Let's start 9-3. That was the easiest section of convergence and divergence test you'll ever see. You're welcome. Which is why we're starting 9-3.
So for the 1/n, like on the ET, would they expect us to know the infinity?
They would expect us to know its definition. You're thinking, I think, of the integral test of 1/x to the p, which is technically one way of proving it, which we'll see today. But you could also on the AP just call it the simple harmonic and say it diverges as one that a lot of kids memorize. That 1 over n is always divergent. But we'll see today as one of the reasons. Actually, 2 of the reasons. Both tests can prove that 1 over n is divergent. The P series is probably the most optional. Be careful. 1 over n, the limit of that is 0. But the limit of the partial sums, aka the infinite series, is 0. Yeah. Huh? What's a number?
A number?
Oh, is it an endeavor? Sorry, I thought you asked if it was a number.
Number.
Some of these are written kind of weird, and there are little places that made little changes, and it's hard to read. So I was trying to see what that had. Yeah, every single test is an endeavor. Which I think we did yesterday too, right? With Geo, did we not label them? We did. Okay. Yeah, I just need to copy this piece. So where are we at? 16?
Yeah.
I had my Google Drive open at some point to get them all organized, and then. Ooh, do you guys see lots of ifs for this one? That means, can we always use it?
No.
Oh, that's okay. We can't always use the geo series. It has to be a geo series first. We can't always use the nth term test. It has to have a limit that's not 0. Well, we can't always use the integral test. Do you see where I'm headed with this? Different functions have different tests that are either built for them or at least are best for them. There are only a few functions here and there where multiple tests could be used. Hence the reason why we have so many different tests. I'll give you your forevers and endeavors up so I can update them. So the 3 ifs are, must be continuous, positive, which means not negative and not alternating. Not negative, not alternating. And decreasing. Must be continuous, positive, and decreasing. Now, guys, hold on. When you see the word decreasing in calculus, what should your brain be doing? Oh, when the derivative is less than 0, and I have to do sign charts, and I have to... We're not going to go through, because remember I told you yesterday, these infinite series problems, they might very well be, hey, you're given this and this and this infinite series, you're given like maybe 3 or 4, and you're trying to figure out which ones are convergent, or which ones are divergent, all in a single multiple choice. Or it could be an effort cube where you have to have logic attached and argue your way. But if it's in a multiple choice and I'm supposed to go through and do them real quick, like 3 different ones, and figure out which ones are and which ones aren't, I have to be able to go fast. So you're not going to necessarily have to write out a paragraph or write out a justification or an explanation as to why or how it's decreasing, which means I don't really want you taking derivatives and doing sign charts to prove that. Instead, do you remember when we first did sequences? So we wrote out the first few terms, the first 4, the first 5. And then didn't you see me yesterday actually give you some terms without a sigma of a series and have you think about, consider, I think it was a geometric series that was written out, a couple of those. Or even on some of the sigmas themselves, every now and then I've written out a few. To figure out the decreasing nature, I'm going to be okay if you write out the first few terms and make sure you understand the numbers that you see. You might be like, why would I not understand the numbers that I see? Well, what if you see an ln of a half versus an ln of 2+1? Do you know which one's higher? Or which one's lower? Or if you have like a subtraction or addition of an ln, like it might just throw you off as far as which one's stronger, ln of a half or 2, or I don't know. Depending on ln is the one that's most commonly used, where it can seem to be decreasing, and eventually it is, but to begin with it goes up a little bit and then down. Those ones are a little bit tricky, a little bit weird that we're going to see. But I'm okay if, in general, we write out a few terms and we realize, oh, we see what's going to happen. Yeah, it's going to keep on getting smaller and smaller. Done. Check. Positive. That should be obvious. No negatives. No alternator. That should be an easy check. Continuous. All we have to do is check for discontinuous. So it's not meant to be like a big, lengthy process of all the ifs, making sure that they're all there. It's more of just a background understanding that we just double check. And if something like, especially the positive or the decreasing, fails, make sure it doesn't fail just for a little bit and then for forever it's fine. Because if it's just for a little bit, then forever it's fine. We can actually split up the bounds, the sigmas, and test for the convergence of this one plus a constant. Convergent plus constant is always convergent. It kind of lets us even work the system a little bit. So what do we see? If a function is a function, if the nth term is written as a function, if the nth term, which is not a function, it's a discrete, but if its function form would be continuous, positive, and decreasing, then we could compare the infinite series of the nth term with the infinite integral, or the improper integral from 1 to infinity of the function. If that integral converges and the series converges, and, which is really cool, because not many tests allow us to do both, and if the integral diverges and the series diverges. So why do we spend time on improper integrals? Because it's one of the tests for series. Use this test when? When it's easy to integrate, or, to be honest, or possible. Sometimes you might have expressions, especially with factorials, you're not able to integrate factorials because they are not elementary functions. If you ever see a factorial, this is not the test for you. You will see them, but this is not the test. The test for factorials is R, ratio. And once again, a quick little reminder, you can put it in parentheses, only positive terms, no alternatives. Okay. We already talked about these just a little bit. I don't think we have to go too much. I'm just going to say something like, write out your first few terms. But I'm going to put a quick little note under decreasing to wash out for ln's. I'll do ln of x. Watch out for logarithms because they can cause us a little bit of trouble. We're not as naturally cognizant of what's going on there. Like e to the, we can kind of picture 2.7 raised to a power. But ln's we're just not as familiar with, which is fine. Watch out for ln's, maybe square roots too, but not as much. We can split up our sigma from k equals 1 to infinity of a sub k to equal k equals 1 to b plus b to infinity. Like let's say it goes negative for a little bit, or let's say it goes increasing for a little bit, but then the infinite part is fine. Then we could do the integral test. We just wouldn't be coming from 1 to, we'd be coming from, I don't know, maybe it's 2 or maybe it's 3, whenever it starts finally decreasing for forever or being positive for forever. We can split it up if we need to, because technically we could plug in like 1 and 2 and 3. We could take the first 3 and say, fine, whatever, constant plus constant plus constant plus convergent. Perfect. Converges. Or constant plus constant plus constant plus divergent. Okay, diverges. So if this fails anything, if we can kind of just go a few terms in and have it pass, okay, we can do that too. We can do that too. But otherwise, continuous positive, you guys know, no negatives. And no alternators. And then continuous. We still have 10 minutes, nice. Continuous. I'll just say check for discontinuities, I think is what I said. If there are discontinuities in the bounds, we're in trouble, but there shouldn't be really any discontinuities in the bounds. Yeah, Joe.
Is this working with negative and
Say it one more time.
is it with negative and increasing? So,
You're thinking of like the reflection, yeah. And the convergence of one should indicate the convergence of the other. I don't have a rationale as to why off the top of my head. Well, if every single term was negative, is that what you're thinking? You could factor out a negative. Yes, but I would ask you, I think yes, but I would ask you to factor out the negative before applying the test, because then it would be positive. I think that's a proper statement. Why can't we use geoseries? To be honest, we shouldn't ever start with geoseries. That's a bad idea. We should always start with the end term test. Start, yeah, because as soon as we start building our category of tests, we're always going to go through the old ones and make sure that they couldn't be used. So let's start with the nth term test. Nth term test, what do you do? Limit. Limit of the sequence equals what? 0. And what happens if it's 0? We don't know anything. Okay, well, nth term test fails. Geoseries. What if we start writing out? If we plug in 1, that'd be 1 over 2. Plug in 2, that'd be 2 over 5. Plug in 3, that'd be 3 over 10. Plug in 4, that'd be 4 over 17. Is that geo? Can I multiply by the same something every time to get the next numbers? Guys, you won't have a geoseries if you don't have something raised to the n power. That could be geo. We'd have to rearrange it a little bit, but that could be geo. This, no. Geo, I need something, some sort of repeated multiplication, some sort of base raised to a power. Raised to a variable power, an exponential. Okay, so nth term fails. Geo fails. Hopefully integral test works, or else we have nothing else to do, and we'll say, well, save it for later. Could the integral test work? Well, let's go ahead and consider, okay? Let's consider the function that would come from this. Let's consider x over x squared plus 1. If this was a function. If it wasn't just an nth term formula, if it was a function. Can't say that this n over n squared plus 1 is continuous because it's only 4 integers. But I can look at this function and say, oh yeah, he's continuous for all real numbers. Is he continuous? Yes. Is he positive? No. But wait, I'm only going from 1 to infinity. Is he positive for all x's 1 to infinity? Yeah, he'd be negative for the others, but no, he's positive for everything within the bounds. And then decreasing. Well, what's going on? 0.5, 0.4, 0.3. Is it going down? Yeah. So therefore I can say that's enough for me. Okay? That's enough for me. And these are numbers that we're used to. So as the numerator keeps on counting up by 1, the denominator is going to keep on growing as it keeps on growing. The sequence, I should be careful. The sequence, the terms are going to 0. But we know nothing about the series until we integrate. So it's time to integrate. Bummer, man. What are you guys going to use to integrate? You sub. You should get to an ln. Go. You sub. You should get to an ln. What was this first name? Oh, got it. Okay, thank you so much. Bye. Oh. Maybe Mrs. Pettit wants to see you in the office. I thought she said you get her. You said, yeah. So did you guys get your 1/2 ln of x squared plus 1? from 1 to b. Do you really need those absolute values? It's always positive. So we end up with ln's going to infinity, so even if ln of b squared plus 1, if that's continually growing, I don't care about the 1/2, I don't care about minus the little baby constant. That's infinite. So what does that mean? Since the integral test applies, why does the integral test apply? We already showed that continuous positive and decreasing, right? And the integral from 1 to infinity of x over x squared plus 1 dx diverges. And just put the idea is okay. The series diverges as what? The integral test applies. I showed that. The improper integral from 1 to infinity of the function diverges, and the series diverges as well. And done. No big deal. Wait a minute. This next one, isn't it basically the same thing? Divergent, right? What's different? Do I still have my continuous? Do I still have my continuous positive decreasing? Did it in the wrong order, I apologize. Am I still going to consider my integral? How am I going to integrate this time? Arctan. Because I have a 1 over u squared plus a squared, right? My a is just 1, so that's no big deal. 1 over a is just 1. Then u over a is just x over 1. I'm going from 1 to b. What happens this time? I end up with pi over 2 minus pi over 4. Is that divergent? Nope. Because that is the convergent, or that is the value that the improper integral converges to. And so therefore, we can say once again, since the integral test applies, why? Continuous positive, decreasing. And the improper integral from 1 to infinity of 1 over x squared plus 1 dx converges. My series converges as well. I need you guys to realize it's not that our logic is flawed, it's just it's going to be a lot harder for our logic to make these deductions of convergence or divergence of infinite series if we don't have a definitive test that we can use that gives us a definitive answer that we can state. We cannot just rely on our natural logic anymore. So we have our n-term test, we have our geo-series test, now we have our integral test, and tomorrow we'll see our p-series test. And then I'll start kind of throwing random series at you to see if you can not only take it, but also pick a test to apply, and then find one that works, and then take a correct conclusion. Lorenzo. What it converges to? Not right now.